1.4 Trigonometric functions of any angle. So far we've sort of limited our definitions of the trigonometric functions and everything that we can do with that to triangles, and that really does limit us. What I mean with that is, in a triangle, all the angles have to add up to 180, so there are some relationships there that limits it. In triangles, you can't have an angle larger than 180 degrees, so can you not find the sine of 190 degrees, for example? And another problem is that you can't have negative angles. And so there is another way to define trigonometric functions, and the first thing that we need to do then is to reconsider what is an angle. Well, one way to define an angle then is to think of an angle as a rotation. So when you do that, so when we think about it as a rotation, we can think of an angle that rotates one direction. So up, for example, would be positive, which would be a counterclockwise rotation, and a negative angle, which would be here. This one is a negative angle. That would be when you go clockwise. Now sometimes I have a little trouble remembering that, or not anymore now, but maybe when I was a little younger. And so let's think about this way. So let's think about, what if we started with the angle along this axis, and we'll consider that here in a little bit again. So this would be the initial side of the ray, right? So I just redrew the picture. So how can you remember that counterclockwise, which is this way, is a positive angle? Well, counterclockwise would say up, right? So, and I just mentioned this, if you go up, then the angle is considered positive. So we took this ray and we rotated it to here. So we started with the angle with the array, with a its ray is fixed at a point. We started with the ray over on the positive x, and we rotated up, and then we ended over here with the ray. So then this would be called the initial side, and this is the terminal side. If you do that again, but now let's go in the other direction. So if you go in the other direction, so we take a fixed point here, we run a ray out of it, and then we rotate it this way, down. So if the initial direction is down, then that's a negative angle. So up is positive, negative. Don't want you to think that you can only rotate one full. So for example, what if I started with the ray again over here? So we have a ray, fixed point, and what if we rotate this way? So all the way through, so we just rotated 360 degrees plus a little bit more. Okay, so when you use rotations, you can get all real numbers in terms of a value that you can find a sine or a cosine or a tangent for, because I can get positive numbers and I can go up, I can go all the way past 360, so you can get any positive number, and the same thing in the negative direction. So let's add a little bit more vocab here. So I already mentioned some of this stuff. The only thing that I didn't mention yet here is the vertex. So here's what we consider then the vertex. So we start with a ray, so this is the initial side, okay, and if I put the initial side on a positive x, then that is considered in standard position. So this is along the positive x-axis, and then in this case we rotate it up, so this is a positive angle, and the spot that it ends to terminate is to finish, right? So the terminal side is the spot that the ray ends in, then this is the positive angle rotation, and the same thing clearly in the negative. Okay? Let's draw a couple of these and see if we can come up with this. So draw a 25-degree angle. So you don't need to have a coordinate system for this, so, and I'll do one without, and then after that I actually like the coordinate system. So if we start with our ray in our initial position here, 25 degrees would probably end somewhere like there, right? So this is a 25-degree angle. This would be a reasonable picture for that. Okay, with if theta is 25, then this is theta. Okay, so what does it look like for 140 degrees? Well, and this is why I like the coordinate system. So for 140 degrees, well, this is a right angle, right? So if we start here, then this would be considered our 0 degree. So we haven't rotated yet. So 0 degrees here. This is 90. And then this would be 180. So 140 is between 90 and 180. It's actually you know, a little bit closer to 180 than to 90. So this might be a good finishing position. So this would exactly be halfway. So let's put it about right there. And then that angle from here to here, that is your theta. So that is the 140 degrees. So how about 270? So 270 degrees puts you, let's see, how far does that put you? So if this was 0, and this is 90, plus another 90, that's 180, plus another 90, that's 270. So 270 degrees ends up on an axis. It ends up on the negative y-axis. Okay? And a negative 45. So negative 45. Well, that would be halfway between 0 and then this would be a negative 90, right? So negative 45 would look like this. You would draw the angle and half it there. And then you would say this is, again, so if that's theta, then your angle is here, and then a negative 290 finally. So looking at that, hopefully you had a little more room on your paper than I did. So let's see, negative 290, right? So that's 0, we're going negative. So negative 90, negative 180, negative 270, so I need 20 degrees more. So that leaves me with like 70 here. So it would look something like this. And then the rotation would come from this direction. So that is theta. So theta is the angle from here to there. Okay? Alright, so now let's put that in terms of a trig function. And I created a little bit of a mess here. Again, I think you're on your next page, so I'm going to try to clean this up a little bit so it doesn't look like it interferes. Alright. So, how can we use this to define trigonometric functions? Okay, so let's say we started over here, and let's say that the angle of rotation that we have was from here to there, so that's theta. Okay, so it's a little bit more than 90, you know, looks to be about halfway. And then you end up with a point here, and when you put this on a coordinate system, then you can actually find the coordinates for that point, right? The coordinates of that point would be found by realizing, that you have an x and a y value at this point. So on the terminal side, we can just fix a point there. And the y value would be the distance from here to there, and the x value would be the distance from here to there. Okay, well, so what I'm doing now is I'm creating a right triangle here. So the definitions of our trig function, okay, is related to a right triangle because you're going to create a right triangle here. And even though the rotation was from here to here, okay, we are going to define the sine of theta based on the triangle that you create with the x-axis. And so we're going to actually look out of this angle here, and the sine of theta then would be y over whatever that distance is. Well, that distance we're going to call r, because think of this as a fixed length now, and if you rotate that you would have a radius of a circle. So the sine of theta is y over r. Some books use an m here as in terms of a magnitude. Keep in mind that you could find r, that can find r because you did create a right triangle, that r squared would be this, so r would be the square root of x squared plus y squared, which would make r always a positive. Yeah? Okay, so the sine of theta is y over r. The cosine of theta would be x over r. It's whatever the x coordinate is divided by the radius, and then the tangent is opposite over adjacent. So now I have a definition for a trigonometric function based on putting a rotation on a coordinate system with a fixed origin, and you should be able to come up with these. And then here, you know, we just flip these, right? Because this is the reciprocal, so that should be an r. So that is r over y, that is r over x, and then this is x over y. Okay, please keep in mind that this is defined this way. Okay, so it is a separate definition from what we've done in our triangles. They are related, because ultimately, to be able to find this, we're going to cheat and make a right triangle. But the right triangle that we make isn't the angle here, it comes from the angle over there. Okay, so let's find the exact values of some trig functions by using special triangles and then the reference angle. And I haven't really spoken about the reference angle, but I'll try to illustrate that here just a little bit. You probably can guess at it. So 120 degrees, this is one reason that we practice drawing them. 120 degrees would be just a little bit more than 90, right? So 90 degrees here, and 120 would be more than that. And 120 degrees would put you here. Okay, so if that's 90 and this is 120, then from here to here was 30, but that leaves you 60 degrees over here. And that's the reference angle. The reference angle is the angle that you're making with, if you draw this triangle, what angle are you making with the x-axis? So it's always to the x-axis. Well, we just covered special triangles, so this is a 30, 60, 90 with the 60 here, so then you know that this is 1, this is the square root of 3, and this is 2. With one small difference, we are on a coordinate system, right? So it's not just 1, this is a negative 1. Okay with that? Okay. So what did I say? I said the reference angle is 60 here. And then let's just use the definitions. So what is the sine of the angle? Well, the sine of the angle then would be the square root of 3 over 2. And the cosine of this angle would be, and this is why the negative was important, it's a negative 1, it's adjacent over the hypotenuse, or the x over the y. It's a negative 1 over 2. I guess I should put that here. So this point here has the coordinates a negative 1 square root of 3. And then the tangent of the angle would be the square root of 3 divided by a negative 1. So that's actually a negative square root of 3. Okay, and then the other 3 we can find by just flipping, right? So 2 over the square root of 3. The secant then would be a negative 2 over 1, so just a negative 2. And then the cotangent of theta would be this one flipped, so a negative 1 over the square root of 3. So those are the values for the trig functions of an angle. Let's do it for 225. So for 225, again, I would draw a picture first. So 225 is past 180, right? So we're going to go and draw a coordinate system. It's a little crooked, but okay. And 225 would be, so if that's 180, 225 would be 45 degrees more this way, right? Because 180 plus 45 is 225. So the overall rotation was 225, but the reference angle that we're going to use is then 45 degrees. So there's your reference angle. I'm going to make this a special triangle, which is a 45 degree triangle, 45 by 45. So this is 1 over the square root of 2. This is 1 over the square root of 2, and then this would be, I'm sorry, I have two things in my mind at this point. Let's make this negative 1, that a negative 1, and then that would be the square root of 2. Okay, then let's find the values of the sine and the cosine and the tangent. So the sine of the angle, and keep in mind that the reference angle is 45 degrees, but the sine of the overall angle would be, let's see, if we're here, the sine is the y value over the hypotenuse. So it's a negative 1 divided by the square root of 2. And the cosine would be the x value here, which is also a negative 1 over the square root of 2. And then the tangent of that angle would be a negative 1 divided by its negative 1, which would be 1. And then you can flip these, so the cosecant of the angle would be the square root of 2 with a negative. And that means that the secant of the angle is the same. And then finally the cotangent, when you flip 1, you still get 1. So those would be the answers at that point. Alright, one more. Hopefully I can not stumble on this one. Stumble a little bit on the previous one. So 330 degrees. So here's a picture for 330 degrees. We're going to put it on a coordinate system, and we're going to rotate 330 degrees. Well, 330 degrees is almost 360, right? Because this would be 360 degrees. You're actually 30 degrees away from it. So sorry about that. So we're 30 degrees away from it. So that would look a little like this, right? And then we're going to make our triangle always to the x-axis. So the rotation that we're interested in is like that's the 330 degrees, right? But that means that the reference angle is this one. It's the angle to the x-axis. So the reference angle here, the reference angle is only 30 degrees. That would make this a -1, this the square root of 3, and this is 2. And I didn't put the coordinates there, but in terms of coordinates then, it's the square root of 3 in the x direction and a -1 in the y direction. So let's see if we can find our sine, cosine, and all that then. So the sine of the angle would be, if you're in this angle, the sine would be a -1/2. The cosine of that angle would be the x over the 2, the square root of 3/2. And then the tangent of that angle would be a -1 over the square root of 3, because it's opposite over adjacent. So a -1 over the square root of 3, and we're just going to leave that. And then we're going to flip these to find the reciprocals. So -2, secant is 2 square root of 3, and then the cotangent of the angle would be a negative square root of 3. Okay. Let's go back 1 second, relook at this a little bit, and realize that we get positive values out of here. Yeah, but it is now also possible to get negative cosines or negative cotangents. And it really is possible to get any of these. So you can get sines and cosines and tangents and reciprocals that are either positive or negative. And what that depends on is based on the definition of the function. And what I mean with that is over here. So if I look at the sine, if the sine of the angle is y over r, and I said that r is always positive, right? Always positive, then this value will be positive, the sine will be positive when the y is positive. Well, the y, if you think of your quadrants, and we'll go through this again at some point, but the y is positive in quadrants 1 and in quadrants 2. So the sine will be positive in quadrants 1 and in quadrants 2. The sine will be negative if you have a negative y, which would be in this quadrant, which is quadrant 3, and the y is also negative in this quadrant. So in 3 and in 4, we have negative sines. Okay? This chart summarizes that for you. Now that's a bit annoying because we have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4 quadrants. You'd have to memorize 24 of these. Okay? Now, honestly, I don't have them memorized either. I just sort of quickly configure it out based on the definitions for sine, cosine, and tangent, and then the other ones I just flip. So I know that if the sine is positive, the one that flips, the reciprocal of this, is the cosecant. Well, that if you flip a positive number, it's still positive. So the cosecant is positive here, and it's negative there. Okay? So how can you guys sort of start memorizing that? Well, there's a little mnemonic there, and that says that all students take calculus, which is not necessarily true, but we're going to use that. And we're going to start in quadrant 1 and then just put the A, the S, the T, and the C down starting in quadrant 1. So this is quadrant 1, that has an A, this has an S, and then this one has a T, and then this one has a C. And the A stands indeed for all functions. So all functions are positive here. So the sine, the cosine, the tangent, and their reciprocals. And that is because both the x and the y are positive. So any of the definitions, And the definitions are up here again, right? So any of these definitions that use x's and y's and r's, they're going to be positive if everything's positive. Okay? So I know everything there is positive. The s, hopefully you've guessed that part, then the s stands for the sign. Okay, so the sign is positive in quadrant 2. Well, if the sign is positive, then the cosecant must be positive as well. Well, that leaves a bunch of other functions. Okay, so which functions do I not have then? Well, I don't have a cosine listed, so that one's negative. And that means that the secant is negative as well, right? And I don't have a tangent listed, so that means that the tangent is negative and that the cotangent is negative as well. So those are all negatives. Okay, how about over here? Well, hopefully, again, you've now sort of starting to figure out that the t stands for the tangent, and that means that the tangent here is positive. Well, if the tangent is positive, then the reciprocal, which would be the cotangent, would be positive as well. So then the other ones, which would be sine and cosecant, those two are negative, and the cosine and the secant are negative. And, you know, you should be able to sort of figure this out. I mean, the cosine, again, the cosine is defined as x over r, and if you're in this quadrant, the x is negative, right? So a negative x would give you a negative cosine and a negative secant. But the y is also negative here, right? So if you think of the sine as a negative y over r, then that explains why it's a negative sign. So how about the tangent and the cotangent? Well, the tangent is the ratio of your y and your x. So if I look at the tangent of an angle and it's defined as y over x, and I have a negative y over a negative x, do you guys see that they cancel that way? So this is why the tangent and the cotangent are positive in this quadrant, because the negatives cancel. Then finally, last quadrant, so the c stands for the cosine. So if the cosine is positive, then the secant must be positive. And then that would leave you with some negative values for your sine and your cosecant, so those are negative. And then your tangent and its reciprocal, the cotangent, must be negative as well. And that hopefully will help you memorize a little bit, or figure this out a little bit when you struggle in the beginning. Okay, again, for me, I do that a little different. So when I was taught this kind of stuff, and my daughter's just starting coordinate systems, and she actually labels them this way to remind her that we have positives and negatives. And so I know the cosine relates to the x, so the cosine is positive here, and the cosine is positive here because I have positive x's, and then the reciprocals, right? I know that the sine relates to the y, and then that means that the sine is positive here and positive here. And the tangent relates between the ratio between y over x, so if both y and x are positive, I have positive tangent here, and if two negatives cancel, so then I'd have a positive tangent over here. And you got the same picture. Alright, thank you.